In this video, I am going to find the slopes / tangents of parametric curves. In general, when we find the slope of a function, let's say our function is y is equal to f of x. How do we find the slope of this function? You just take the derivative with respect to x of both sides, right? So that is going to be dy over dx is equal to df over dx. Very simple, which is nothing but f prime of x, and that is the slope. And typically slope is denoted by m. However, in our case, things are slightly more complicated. Our x, right here, x in and of itself is dependent on another variable t. So what it is, it depends on a parameter, which is t. So x is going to be g of t. That means x is a function of t. So my equation y is equal to f of x. This in essence becomes y is equal to f of x. But instead of x, I'm going to put g of t. So it becomes f of g of t. Now this is something you have seen before. It is function composition or composition of two functions. That means we have two functions f and g. We define composition of f with g of t as f of g of t. Now, in order to find the slope, we need to do the following. We need to take the derivative like the way we did right here. So we are going to take the derivative of y. However, it's going to be with respect to t. So dy over dt is going to be d over dt f of g of t. Now, this is a function composition, and we could use the chain rule to find the derivative of composed functions. Now, if we apply the chain rule, this is what I am going to get. df over dg, g is actually g of t, right? Times dg over dt. Now remember, my g is nothing but x, right? So I will have df over dx, right? Times dx over dt. This is the Leibniz notation for chain rule. Just to clarify, now f is nothing but y, right, in our case. So this is going to be dy over dx times dx over dt. So now look, we started right here, and this thing is equal to this. Now between these two, if we solve for dy over dx, so we will have dy over dx is equal to this divided by that. So that's going to be dy over dt divided by dx over dt. Now this is the formula for finding the slope of parametric curves or slope of parametric equations. Now, let me go ahead and apply this concept, apply this to a specific example to clarify the concept. So let's say our simple parametric equations are this. X is equal to cosine of t and y is equal to sine of t. By the way, this represents unit circle. Okay, if you graph it, this is how it's going to look like. So this is going to be the unit circle. All right. So now let's say, for the sake of argument, we want to find the slope at this particular point, and at this point, let's say t is equal to pi over 4. And here we kind of restrict t to be between 0 and 2 pi. 0 is less than equal to t is less than equal to 2 pi. Now, in order to find the slope or tangent at this point, we are going to go ahead and use this formula. So at this point, the slope is going to be dy over dx. Okay, let's just use m here. M is equal to dy over dx times equal to dy over dt over dx over dt. Now, our y in our context is sine of t. So the derivative of sine of t with respect to t, which is dy over dt, is going to be nothing but just cosine of t. And in the denominator, we have dx over dt, derivative of x with respect to t, or derivative of cosine of t with respect to t, is going to be negative sine of t. So which becomes negative cosine of t over sine of t. So my slope in essence becomes m is equal to negative cosine of t over sine of t. Now let me evaluate this at the point of interest. So for t is equal to pi over 4, so my slope is going to be negative cosine of t over sine of t evaluated at t is equal to pi over 4. Now, as you know, cosine of pi over 4 and sine of pi over 4, they have the same value, which is square root of 2 divided by 2. So that's going to give me nothing but negative 1. Okay, so my slope in essence is m is equal to negative 1. So this is a value I will need. So the slope of this tangent line, okay, so this was the point of interest right here. So the slope of this tangent line right here on the unit circle is negative 1. Now that we found the slope at the point of interest, let's find the equation of the tangent line. And we are going to use this formula for straight line. You have seen it before. You probably do remember y minus y naught is equal to m times x minus x naught is the equation of a straight line, given that you have the point x naught, y naught. And that's something we could easily find. My point of interest is t is equal to pi over 4, right? T is equal to pi over 4. So my x naught is going to be cosine of pi over 4, that is going to be nothing but square root of 2 over 2. And similarly, my y naught is going to be sine of pi over 4, which is also square root of 2 over 2. Now I can go ahead and apply these two values, x naught, y naught, which is square root of 2 over 2, comma square root of 2 over 2, into this equation. So that's going to give me y minus square root of 2 over 2 is equal to slope m, which is negative 1, times x minus square root of 2 over 2. Now I can go ahead and simplify it by multiplying everything by 2. So that's going to give me 2y minus square root of 2 is equal to negative 2 times x minus square root of 2 over 2. Now, if I simplify it further, this is what I get. Okay, so this is going to be the equation of the tangent line. Now, I'm gonna talk about couple of special cases. By slope, by the way, is equal to negative cosine of t over sine of t. One special case is horizontal slope. Horizontal slope. When is my slope going to be horizontal? That means when slope is 0, when m value is 0. So that means if your cosine of t is equal to 0, but remember, we don't want to have a situation 0 over 0, right? So we have to make sure that we are looking at values where sine of t is not equal to 0, but cosine of t is equal to 0. That will give you the condition for horizontal slopes. Now, as you know, it's pretty easy. Cosine of t, when is it 0? It is going to be 0 when t is equal to pi over 2 or 3 pi over 2. So these are the scenarios where you will have horizontal slopes. Now, the other condition is vertical slope. Okay, so vertical slope. Now, in that case, what do we have to have? We have to have the slope undefined. That would happen when your sine of t is going to be equal to 0. But remember to make sure that cosine of t is not equal to 0. Otherwise, we will have 0 over 0 situation. Now, for what values of t, sine of t is going to be 0? It's obvious, right? It's going to be t is equal to 0 or t is equal to pi, right? These are the two values. All right? So these two values would give you vertical slopes. Now, let me consider a third scenario where we are going to figure out the concavity of the parametric curves. You probably do remember that concavity is found by taking the second derivative, right? That is to say that we are finding d square y over dx squared. That's going to give us the concavity. If this is positive, it's concave up. If it's negative, it's concave down. Let's first find the formula for parametric equations for the second derivative. So we already know that dy over dx is equal to dy over dt over dx over dt. Now, what if we were to do this? This y, if we were to replace y by dy over dx, then what happens? On the left-hand side, you're going to get something like this, d over dx of dy over dx. That is what you're going to get. Now, by using this definition or this formula, we are going to do the following: d over dt of dy over dx divided by dx over dt. This, by the way, in essence, the formula for second derivative. So the left-hand side is nothing but d square y over dx square. That is going to be equal to d over dt of dy over dx, all of it divided by dx over dt. Now, this formula we are going to use to find the concavity. In the example that we were talking about, our slope was m is equal to negative 1, right? At t is equal to pi over 4. Now, we use the slope m is equal to negative cosine of t over sine of t. This, in essence, is our dy over dx, correct? So I'm going to take this and plug it into this. So my second derivative, d square y over dx square, is going to be d over dt of dy over dx, which is negative cosine of t over sine of t, all of it divided by dx over dt. Remember, x was cosine of t, so dx over dt is going to be negative sine of t, which, by the way, is nothing but this is going to be negative d over dt cosine of t over sine of t divided by negative sine of t. If I simplify it, I'm going to have d over dt cosine of t over sine of t, all of it divided by sine of t. Now, if I simplify this thing by using the quotient rule and do the algebra, at the end I get d square y over dx square is equal to negative 1 over sine cube of t. So that's the second derivative. Now, whenever this thing evaluates to positive number, is going to be concave up the curve. I mean, the parametric curve is going to be concave up. On the other hand, if you have negative number, okay, the parametric curve is going to be concave down. Now, when am I going to have positive value for the second derivative? Whenever sine cube of t is negative. Why? Because there is a negative in front. So negative and negative is going to make it positive, right? So whenever sine cube of t is negative, it's going to be concave up because the second derivative is going to be positive. On the other hand, whenever sine cube of t is positive, the second derivative because of this negative is going to be negative, right? So in that case, it's going to be concave down. Now, finally, let me summarize what we talked about. So we talked about finding the derivative, right? dy over dx for parametric curves. Then we talked about the conditions under which the slope or the derivative is going to be horizontal, right? So horizontal case. And then we talked about the vertical case under which conditions the parametric curves are going to have vertical slope. And then we talked about concavity of the parametric curves by taking the second derivative of the function. I hope that this discussion was helpful. Thank you very much.